we're going to explore other properties of matrices that are going to help us solve matrix equations, including the zero and identity matrices, and being able to find the determinant and inverse of a square matrix. This segment is going to focus on finding the determinant and inverse of a square matrix. So let's start with the multiplicative inverse of a matrix. What is it and why do we need it? Well, the multiplicative inverse is a matrix that we can multiply another matrix by to get the identity matrix. In other words, if we have a matrix, let's call it A, and we multiply it by that thing, we get the identity matrix. The equivalent to that in the number world is, say we have a number like 3, we have a multiplicative inverse of 3 is 1/3, because when we multiply 3 by 1/3, we get 1. Similar kind of thing for the identity matrix. If we multiply a matrix A by an inverse, multiplicative inverse, we get the identity matrix, which is a matrix with zeros everywhere except for ones in the main, what we call the main diagonal. It's like for a 2 by 2, you know the identity matrix has the ones here. For a 3 by 3, the ones are again down that main diagonal. Same thing for an n by n matrix. So why do we need the multiplicative inverse? Well, in algebra, if we have 3x equals 27, and we need to solve for x, get x by itself, we're going to multiply both sides by 1/3. 3 times a third, 27 times a third, to isolate the x. In a similar way, with matrix algebra, if we have a matrix A times x equals b, and we want to get x by itself, and oh, by the way, x could be a number or a matrix, the way to do that is by the multiplicative inverse. We're going to multiply A by its multiplicative inverse and multiply the other side by the multiplicative inverse of A to isolate the x. Because remember, A times A inverse gives you that identity matrix, which is like 1. So how do we find this multiplicative inverse? Well, if A times the multiplicative inverse of A is equal to the identity matrix, we can find the multiplicative inverse by turning the matrix A into the identity matrix. And that involves a series of row operations to turn each of these elements, whatever they happen to be, into their respective counterparts over on the identity matrix. Now, that is beyond the scope of this course, so we're going to kind of take a shortcut here and show you how to find it for a 2 by 2 matrix. Okay, and our joke of the day is from Happy Face Math. So for a 2 by 2 matrix, if we try to figure out what that multiplicative inverse of A would be, and we did a series of operations, we would find that the multiplicative inverse is 1 over A times D minus B times C of the original matrix times a new matrix where A and D on the main diagonal are reversed, and B and C on this opposite diagonal just have negative signs in front of them. And again, the derivation of that is beyond the scope of this course. It turns out this number right here, AD minus BC, is a special number we call the determinant, which is used for not just 2 by 2 matrices, but much farther beyond it. So a quick sidebar to talk about the determinant, because it actually has applications beyond just finding the matrix inverse. The determinant is found by summing the products of a matrix. So if we have a 2 by 2 matrix, like matrix A here, with terms A, B, C, and D, the determinant of A, which can also be written with bars like this, almost like absolute value bars, and it can also be written DETA, both of those are terminologies for using the determinant, is equal to, we go along each of the diagonals, A times D minus B times C. So let's do an example of finding the determinant for a 2 by 2 matrix. So suppose we have a matrix A with these elements. The determinant of A is going to be 3 times 5 along the main diagonal minus 2 times negative 4. So it's going to be 15 minus negative 8, or positive 23. That would be the determinant of A. Now it's important to note that if the determinant is 0, that means the matrix is singular. And if it's singular, it will not have an inverse. But in this case, determinant of A is 23, not 0, so it's non-singular. It is going to have an inverse. So let's extend our example with matrix A, and let's say we wanted to find matrix A, the inverse of matrix A. So we already know the determinant is 23. It's 3 times 5 minus 2 times negative 4. So the inverse of A is going to be 1 over the determinant of A times that special modified matrix where the main diagonals elements are reversed and the opposite of the main diagonals have a negative sign in front of them. Notice that means that the 2 becomes a negative 2 and the negative 4 then becomes a positive 4. So A inverse is equal to 1 over 23 times that modified matrix, which if we multiply that scalar 1 over 23 times each of those terms, we get the final answer that A inverse is equal to 5 over 23, 4 over 23, negative 2 over 23, 3 over 23. How could we check our work? Well, we ought to be able to multiply A times A inverse and get the identity matrix. And if you go through and you multiply each of those terms using the rules for matrix multiplication, if it's correct, you will get the identity matrix. Couple of notes before we close things out. First of all, inverses and determinants really can only be found for square matrices, where the number of rows equals number of columns. Some square matrices don't have an inverse. Again, we call those singular. That's when the determinant equals 0. And finding inverses for 3 by 3 or larger matrices is really beyond the scope of this course without technology. In class, we're going to show you how to use technology to do this. This gets more into the scope of what a course that's called linear algebra. So that's the determinant and the inverse of matrices, which we're going to use to solve matrix equations.